This is the Messerschmitt ME-163 Comet, a plane capable of reaching 1,000 kilometers per hour, built without landing gear and fueled with chemicals that could kill the pilot long before the enemy ever could. Developed by German engineers, this rocket-powered interceptor was one of a kind, the first aircraft in history to use a rocket engine to achieve unbelievable speeds. But despite its brilliance, this aircraft was as dangerous to its enemies as it was to its own pilots. Join us as we uncover how this extraordinary machine was built and what it was like to fly into combat. You're watching Presage. Hit subscribe and let's dive in. The Comet had a truly unique design, engineered for one purpose: maximum speed and agility. It was a small, compact aircraft where every inch of space was dedicated to performance. It was almost half the size of a typical fighter, measuring 5.7 meters in length, with a wingspan of 9.3 meters and a height of only 2.5 meters. Its empty weight was about 1,900 kilograms. Fully fueled, armed and crewed, it nearly doubled that, tipping the scales at around 4,000 kilograms. For control, the aircraft used elevons on the outer sections of the wings. These were made from wooden frames covered with fabric and then coated with a special finish to improve durability and resist wear. They combined the functions of elevators and ailerons, controlling both pitch and roll. Trim tabs were located on the inner sections and were used to fine-tune the pitch of the plane, reducing the pilot's workload during flight. The landing flaps, located on the underside of the wings, acted more like aerodynamic brakes, simple aluminium plates that helped slow the aircraft during landing. Control of the main flight surfaces was entirely mechanical. Using the control stick and rudder pedals, the pilot transmitted force through a system of push rods and linkages, which directly moved the corresponding control surfaces. There were no hydraulic or electronic assists. Every input was transferred physically. The landing flaps were operated by a dedicated hydraulic system. Control was divided between two levers. One selected the flap position, while the second lever executed the movement itself. To precisely balance the aircraft in flight, the pilot used trim tabs controlled by a manual trim wheel. By turning the wheel, the pilot could adjust the deflection angle of the trim surfaces, reducing control stick pressure and improving overall stability. External armor on the aircraft was minimal. The only armored element on the aircraft's skin was the nose cone, designed to protect the pilot and the main onboard equipment from the defensive turrets of enemy bombers. It was 15 millimeters thick and made of hardened steel. Despite its modest thickness, the cone's sharp angle greatly increased the chances of incoming rounds ricocheting off. Inside the cockpit, the pilot was protected by a 90mm armored glass panel in front and 3 steel armor plates behind. 13mm behind the head and seat, and 8mm behind the shoulders. The cockpit of the Comet was surprisingly spacious, especially for a single-seat fighter. Everything the pilot needed was nearby and easily accessible. It was designed as a tightly organized workspace optimized for brief, high-risk missions where situational awareness and rapid decision-making mattered more than pilot comfort. To ensure the pilot could breathe at high altitudes, the plane was equipped with an oxygen system, a cylinder behind the seat connected to a regulator and mask. Providing oxygen was essential at altitudes greater than 5,000 meters. In addition, the unique rocket fuel emitted corrosive fumes, often causing the pilot's eyes to burn. To reduce the concentration of these vapors, The cockpit was ventilated through an air intake in the nose of the aircraft, which directed fresh air into the cabin, passing through the aircraft's beast engine on the way? Isn't that the engine? Well, where is it then? Oh, my apologies. Passing through the generator and cooling it down along the way. Now for the electrical system. The aircraft didn't require much electrical power, so its electrical system was kept to a minimum. A 24-volt battery and a 2,000-watt generator. The battery was only on the ground during takeoff. Once the aircraft gained altitude, all power came from the generator. Many of the aircraft systems were purely mechanical and required no electricity at all. The fuel system was one of the most dangerous parts of the entire aircraft. Its rocket engine required two extremely volatile substances, which would ignite on contact with each other or organic material. The fuel known as C-stuff and the oxidizer, T-stuff. Several fuel tanks for both substances were located inside the fuselage and wings. To reduce the risk of accidental contact in case of a leak, the tanks for each component were placed in completely separate sections of the aircraft. C-stuff was stored in the wings inside 4 unprotected steel tanks coated with glass enamel, 2 in each wing. The main tanks each holding 177 litres. They were located behind the spar, while 2 smaller 73-litre tanks were installed ahead of it. T-stuff was hydrogen peroxide at an extreme concentration, turning a familiar chemical into something very dangerous. It was stored in 3 aluminium tanks inside the fuselage. The main unprotected tank of 1,040 litres sat near the aircraft's centre of gravity, while the 2 smaller 60-litre protected tanks were positioned inside the cockpit. They were added to maintain balance as fuel was consumed. Precise weight distribution was critical. Even a 2 to 3% shift in the centre of gravity could have catastrophic consequences. It's worth noting that these 2 tanks were located extremely close to the pilot, and as mentioned earlier, the oxidizer was so concentrated that even a brief contact with it could cause serious chemical burns. And in larger amounts, it could quite literally dissolve human tissue. Refueling the plane was an extremely dangerous process. To prevent the slightest chance of the 2 components mixing, the process was carried out separately and in strictly defined sequence by 2 different ground crews. Every pipe connection and tank was carefully checked for leaks, then thoroughly rinsed with water, since fortunately both fuels were water-soluble. Once washing was complete, actual fueling began. Special refueling trucks were used for the task. The oxidizer T-stuff was filled first, poured carefully into the tanks through openings on top of the fuselage. Throughout the process, the refueling area and even parts of the aircraft itself were continuously rinsed with water. After the oxidizer was safely filled, the truck was moved away, and the entire area was washed again to remove any traces of the substance. Only then was the fuel C-stuff filled in a similar manner. The engine Walter HWK 109509, used in the Komet, was a remarkable technological achievement for its time. It delivered incredible thrust and speed, but demanded equally innovative and unconventional engineering solutions. Let's take a closer look at how the engine worked. Most early versions of the engine required a gearbox connected to an external electric starter to begin fuel injection and ignite the system. However, engineers soon realized that this wasn't an ideal solution. The gearbox used for startup added unnecessary weight to an aircraft that relied on every kilogram of performance. That's why we'll focus on a later modification of the engine, one capable of starting on its own. The engine start sequence began with the oxidizer Takeoff flowing from the small starting tank into the steam generator by gravity. Inside the generator were porous stones soaked with a special catalyst. When Takeoff came into contact with these stones, it decomposed violently, releasing a large amount of steam. The steam drove a turbine fuel pump, which initiated the main fuel supply to the engine and gradually increased the flow of Takeoff back into the steam generator, spinning it even faster. As mentioned earlier, the engine ran on two separate components, the oxidizer Takeoff and the fuel Takeoff. The turbine pump was designed to feed both substances simultaneously, but through completely independent channels. Each component passed through its own regulating valve, functioning somewhat like a gearbox with 3 stages. The amount of fuel delivered depended directly on the position of the throttle lever, which was mechanically linked to the valves by rods and levers. After regulation, both components were routed through separate pipelines into the combustion chamber. There, several groups of injectors sprayed the liquids in a fine mist, ensuring efficient mixing and an instant chemical reaction, releasing an enormous burst of energy that produced thrust. The temperature inside the combustion chamber reached nearly 2,000 degrees Celsius, almost twice as hot as lava, and with pressures around 20 atmospheres. The chamber itself heated up to extreme levels, so part of the Takeoff fuel was diverted through a cooling loop. Before entering the chamber, it passed through a metal jacket surrounding the combustion area, absorbing excess heat. It then returned into the main circuit through a filter that removed any of the impurities to prevent clogging. The engine produced an immense amount of thrust, giving the aircraft an unprecedented climb rate of about 80 meters per second, and easily allowing speeds of up to 700 to 800 kilometers per hour, with a maximum speed of 960 kilometers per hour. On one occasion, it even set a world record. Later, one of the famous test pilots of that time described the flying Comet as, "It was fascinating, like thundering through the sky sitting on a cannonball."
Wie schnell? Ja.
The Comet could reach an altitude of 10 kilometers in just 2.5 minutes. For comparison, a modern passenger airline needs about 15 to 20 minutes to climb that high. However, the fuel supply lasted only 7 to 8 minutes of powered flight. After that, the aircraft became a glider, continuing its mission without thrust. In practice, this was sometimes a blessing. As long as there was fuel left, the Comet was effectively a flying bomb. The combination of Takeoff and Takeoff was so volatile that even a minor leak could cause an explosion. That's why, when a pilot knew the remaining fuel was no longer needed, he would open a special valve to dump the leftovers through an emergency system. Even so, stories of comets exploding on landing were not uncommon. It was the price paid for record-breaking speed and extreme innovation. Communication between the pilots and the ground control was maintained through the FUG-16 Zoo radio set, standard for late-war Luftwaffe fighters. The control units were located inside the cockpit, and the pilot connected them via a cable attached to the microphone on his neck. The primary antenna was a mast mounted on top of the fuselage with an additional one built into the leading edge of the vertical stabilizer. For identification, friend or foe, the aircraft used the FUG-25A Erstling transponder. It automatically responded to interrogation signals from Luftwaffe radar stations, sending back an encrypted code. The antenna for this system was mounted beneath the left wing. The Comet was armed with two 30mm Mark 108 cannons, mounted in the wing roots and connected to pneumatic loading system, each gun weighing around 60 kilograms. The firing and reloading systems consisted of 4 compressed air bottles, 2 on each gun, that handled reloading and cocking before each shot, along with the relay box and the electric trigger unit. To arm the weapons, the pilot pressed the main power button on the control panel and switched the main selector on the ammunition indicator. This sent air from the lower bottle to chamber the first round. If a gun jammed or failed to cycle, the pilot could press a secondary button on the side of the control stick to perform a manual pneumatic recharge. Ammunition was fed to the guns through chutes leading from the ammo boxes. The rate of fire was fairly low, about 600 rounds per minute, but the real punch came from the ammunition itself. The high explosive carried nearly 90 grams of explosives each. A single hit was often enough to literally tear an enemy aircraft apart. The Komet only carried around 60 rounds per gun, barely 6 seconds of continuous fire. The takeoff and landing system was highly unusual. Instead of a conventional landing gear, the aircraft used a steel skid, a tailwheel, and a jettisonable two-wheel takeoff dolly, all operated by the pneumatic system. The pneumo-hydraulic system used 3 compressed air bottles and an oil reservoir, all tied together and connected to the 2 actuator cylinders through a network of lines. The system stored enough energy for only 1 or 2 cycles, meaning the skid could be raised and lowered only a limited number of times, and if there wasn't enough pressure left to deploy it, one of the air bottles served as an emergency supply and was charged to the highest pressure, 130 atmospheres. The pilot could activate it by opening a dedicated valve in the cockpit, but once used, the skid was essentially locked into the extended position and could no longer be retracted. In total, around 370 aircraft were built in various versions over the course of the war, but it never became the superweapon it was meant to be. In fact, it never even became a good one. Depending on the source, the total number of aerial victories ranges from 9 to 16 aircraft, while combat losses of the Komets themselves were around 14 vehicles. But most losses occurred on the ground, or as a result of flight accidents and numbered dozens. In the end, it wasn't the Allied forces that became the downfall of this aircraft, but the logistical nightmare required to operate it. Fuel was always in catastrophic shortage, and just getting the aircraft into the air demanded a specially trained team of mechanics and engineers. And all of this effort went into a machine that could stay airborne for only a few minutes, make 1 or 2 attack runs, and then turn into an unarmed glider. The Komet became a reminder that a brilliant idea and record-breaking performance don't automatically make it something effective. At its core, the Komet was so far ahead of its time that it was quite simply useless. What do you think? Was the Komet a brilliant idea ahead of its time, or a dead end from the start? Subscribe to our channel so you don't miss the next episode. And if you enjoyed this breakdown, share your thoughts in the comments. We'll be glad to answer your questions there.